Engineering 305 example problem 6-2. That's the second problem in chapter 6. A hollow steel shaft with an outside diameter of 400 millimeters and an inside diameter of 300 millimeters is subjected to a torque of 300 kilonewton meters. I don't know how big that is at all. 300 kilonewtons. I mean, a newton is... this is big. As shown in figure 6.8. Oh, I didn't look at the... I should go grab that figure. I have not... I didn't even look at that. The modulus of rigidity for steel is 80 gigapascals. So I'm going to put G... I'm going to shrink this. And I'm going to put G is equal to 80 gigapascals. That's for steel. And I'm going to put... OD is 0.4 meters, and the ID is 0.3 meters, and and I've got a torque. That's my last given, my torque, and that's capital T, 300 kilonewton meters. Okay. Let's not even go look at the figure. We have a system where we're twisting it, and I've got a torque, and I've got diameters, I've got geometry, and I've got a material. Right? Is that enough to fill out our equation? Well, sure. Let me pull up our equation. There it is. So the things we're going to need, the maximum shearing stress is this TC. All right, so I'm writing that down behind you. The shear at C is equal to TC over J. I need to know what J is. J is this formula here. So that is going to be J is equal to pi over 2 radius of the outside to the fourth minus the radius of the inside to the fourth. All right, and let's see. C, I know what that is. So I've got T, I've got C, I've got J. I can calculate the maximum shearing stress. That's part A. I'm all set. So I'll hide the equations. There's that. That's what I'm working on. The biggest thing I think on these is going to be making sure that I'm working with the radius and not the diameter. But that's easy enough. Equal to pi over 2 times 0.2. I substituted. I divided by 2, right? Not too challenging. 0.2 meters to the fourth minus 0.15 meters to the fourth. And that's going to be equal to... All right, got to get out the calculator. Pause. All right, so there you go. It's 1718 E negative 6 meters to the fourth. Now, if you did millimeters, it would be 1718... No, it wouldn't. It would be 1.7. Oh, I always get so confused. There would be a difference of 12. So, it's a mess. That's why I just tend to work in meters. It really makes my life easier. Shear is equal to TC, that distance to the extreme fiber. Oh, I know what T is. T is 300 kilonewton meters. C is 0.2 meters. And then J is 1718 E negative 6 meters to the fourth. So I'm going to start canceling out meters. Cancel with meters makes that a squared. And then I've got newtons per meter squared. So that gives me, at least as far as my units goes, it gives me kilopascals. And then I've got to do 300 times 2 for 600 divided by 718 E negative 6. And I'm going to get 34,000, 34.9 E3 kilopascals. Or you might as well just write this as 30. Well, I would actually write it as 35 megapascals. All right. You can't see that because of my mug. Sorry. 35 megapascals. That's part A, the maximum shearing stress in the shaft. Okay. Then they ask, sorry, so then we go back up to the top. So there's our first, right? Get out my sparkly and box my answer. All right. I got that done. Now I got to look at B. The shearing stress on the cross section, the shearing stress on a transverse cross section at the inside surface of the shaft. So now, instead of asking for the maximum or the shear at C, they're asking us for the shear at R equal to 0.15. That is on that inside surface. All right. Well, that's really going to be the same problem, except this formula that I had, and I'll pull up the equation sheet. The formula is now, I can't highlight it. Maybe you can see, I think you can see my mouse. At any radius, the shear at any radius, remember rho is equal to the radius, is equal to, I got to just put in rho instead of C. Well, when I take this equation and put in, substitute 0.15, right? That's going to become, now it's 0.15. Well, that's 3/4 of what it was, so my stress is just going to be 3/4. I don't really think that's something I need to calculate. I would divide that by 4. I'd get about 9, and so I subtract 9, it's about 26. And so I would round that and say 26 megapascals. Now, that is my way of doing it, because I know I'm going to put a safety factor on it. I'm going to do all this other stuff. So if we wanted to go through this and really calculate it, and do a better job, really it would be 35 times 0.75. I will tell you that the book answer for this, is 26.2 megapascals. I am sticking with my subtract 9 solution, because 1/4 of 35 is pretty close to 9. Again, I got my bug in the way. All right. Problem statement. The shearing stress, we did that. Last one. The magnitude of the angle of twist if it's 2 meters long. Do we know our equation? I got my secret button there I can push. Theta, down at the bottom, theta is equal to TL over GJ. Theta is equal to TL over GJ. Yeah, I wrote it in sparkly pencil. Torque was equal to 300 kilonewton meters. L, they just told me it was 2 meters long. J, I calculated that up above, 1718 e negative 6 meters to the 4th. And G, you can still see it at the top of the page, 80 gigapascals. 80 gigapascals. So I want to go through the exercise of crossing out units, double checking my units. Meters and meters are going to give me a meter squared there. And then this whole term, kilonewtons per meter squared, is a pascal. So I've got pascals on the top divided by pascals on the bottom. So I'll just go like this is going to cross out with pascals. But I have to leave the giga. I didn't cross out the giga. Well, I've got a kilo and a giga. And so what does that leave me with? A mega? Yeah. Leaves me with a megapascal. So that's going to go there, and a kilo and a giga. All right. And I almost overlooked the whole kilogiga thing. So so that's a mega, and here's an e to the negative 6. So actually that's going to cross out. So now I've got 300 times 2 over 1718 times 80. Do I have any units at all? No, because I'm in radians. So that's pretty cool. So I can multiply that out. And what I'm going to get, sorry, had to double check my stuff there. What I'm going to get is theta is equal to 0.0044 radians. I might go, at 0.0437, 3 significant figs, sure, box it, call it good. There, now we did. Now, if you kind of go back to what we had been doing, normally on the early problems in Chapter 5, we calculated a stress, a normal stress, and a displacement. And now we've done a normal stress and a displacement. But let's not stop here, because example problem 6.3 is another wedding cake problem. So you got to do the wedding cake problem. It's a cheap one, though. It's vanilla chocolate. There's no cheesecake. Don't worry, more to come.